Hello friends, hope you are doing well. In this video, we are going to discuss about copper extraction. We're going to start with concentration of the ore, followed by the roasting and smelting of the ore, and then the converting step where we produce our blister copper, and followed by the refining of this blister copper using these two methods, fire refining and electrolytic refining, followed by we're going to see other methods of extraction of copper like electrolysis and cementation of copper. Let's look at the concentration of ore, friends. This includes two basic steps. One is crushing of the ore because we need to free our ore particles from the gangue materials. And we need to understand that the ore that we get in the earth's crust consists of only 0.5 to 2% of copper. So you can understand how less concentrated the ore is. It usually found with other sulfates like lead sulfide, zinc sulfide, many other precious metals and along with a lot of gangue. So first step we crush, and by crushing, what we are doing, friends, we are decreasing the particle size, which means increasing the surface area, which in turn helps in froth flotation. We know froth flotation means by modifying the properties, surface properties, we can separate out the ore which we want. Differential flotation, as we discussed in our previous videos, helps us to concentrate one particular sulfide ore, and here we take our CuFeS2 as our main product from differential flotation. By this method, we can go from 0.5 to 2% copper to directly 15 to 35% of copper. This is a huge improvement in the concentration of our ore. Friends, second step is roasting. We usually do this in reverberatory furnace. During this step, moisture and many other impurities and other volatile matter are being removed as a volatile oxides. Friends, here we need to understand our reactant is solid and the product is also solid. So the product that we get after this step is solid. So all those oxides which are volatile, they got removed. But what about some oxides which are not volatile? So they are already in this solid. We have our concentrate along with some non-volatile oxides in this as well. In this step, friends, by controlling partial pressure of oxygen, we partially oxidize iron sulfide to iron oxide. We do not want complete oxidation of iron sulfide. So here, when iron sulfide concentration is very high compared with copper sulfide, then only we go for roasting step. This step is we usually skip if the concentration of iron sulfide in the ore is not extremely high compared with copper sulfide. Friends, during this stage, a lot of sulfur dioxide, concentrated sulfur dioxide is being evolved. Like this, a lot of reactions takes place during the roasting step, and this sulfur dioxide is highly concentrated because we can use this sulfur dioxide for the production of sulfuric acid. So there is a setup to collect sulfur dioxide and it is sent to the generation of sulfuric acid. So friends, by the end of roasting step, we have copper sulfide plus iron sulfide along with the solid gangue or the solid oxides which were not able to get removed as a volatile oxides in this step. Friends, during smelting, we take the roasted ore and we add flux, which is lime or sand, and hot air. These are our reactants. During smelting, we go to high temperature, where this temperature is greater than the melting point of the slag and the melt. Our product is liquid, friends. Earlier, during roasting, we got product as a solid, which consists of many metal oxides as well. In this step, we get liquid made along with slag. The reactions in these are, friends, one more important thing, iron has more affinity for oxygen than copper. Even if copper sulfide gets oxidized to form Cu2O, iron sulfide reacts with copper oxide and converts again into copper sulfide and iron oxide. And this iron oxide helps to fix SiO2 by forming FeSiO3. If there is insufficient iron sulfide or iron oxide in the system, then only we add calcium oxide as our flux. If sufficient iron oxide is there, then there is no need to add lime during smelting process. Friends, in this step also, we do not go for complete oxidation of iron sulfide to iron oxide because iron sulfide has an important role during the converting step. So as far as we try to remove all the slag, all the solid oxides that were there in our solid material along with some removal of iron oxide which helps in the formation of slag. In this step also there is a removal of pure or concentrated sulfur dioxide. So here also there is another setup to collect sulfur dioxide and send it to the sulfuric acid plant. Friends, during this process, we are always talking about controlled or partial oxidation of iron sulfide because we do not want higher oxides of iron to form Fe2O3 or Fe3O4. They do not form slag, they do not properly mix with the slag. So we always want iron oxide to be present and not hematite or a magnetite kind of oxides. So for this, we always give some amount of iron sulfide. So whenever there is a higher oxide is forming, it again reacts with iron sulfide and in turn then they give FeO. FeO is very good, it properly fuses with the slag and helps in the separation of impurities very well. This is also a function of presence of some iron sulfide. Friends, earlier we realized concentrated sulfur dioxide is the product of roasting as well as smelting. So if we are doing both are in two different furnaces and it is difficult or it is not economical to have a separate setup for collection of sulfur dioxide here and as well as separate setup for the collection of sulfur dioxide here. So people, what they found is both these processes are combined in flash roasting, where we allow our ore particles to fall through the air And when they are in the suspension, when they are in the mid-air, they get roasted and produce liquid matte and slag in one step. And another economical step is the generation of complete sulfur dioxide. In this step, can be sent to the sulfur dioxide plant. So this is more economical. So the new plants which are coming up, they're trying to set up a flash roasting instead of roasting and smelting as a two separate steps. Friends, the next step is converting or bessemerization step. Friends, converting, the name itself suggests that you do not need any external source of heat. By converting converting iron sulfide to iron oxide gives heat which is sufficient to keep both slag and metal in liquid state. Just like basic oxygen furnace, there we use steel making converter, there also we do not require any external heat, their heat is generated by the oxidation of impurities. So the name itself says converting means you convert some reaction, some iron sulfide into iron oxide. It generates heat which is sufficient for the progress of the reactions. As long as iron sulfide is there, copper sulfide does not get oxidized because iron has more affinity for oxygen. So the first steps are these, friends. This is the slag formation step. Iron sulfide consumes oxygen, produces iron oxide and sulfur dioxide, and this in turn helps in the fixing of SiO2 by forming 2FeO SiO2. After removal of complete iron sulfide, now we are left with a slag layer and Cu2s. This, because of its appearance, we call it white metal. Now its oxidation begins. Now Cu2s reacts with oxygen, producing Cu2O plus SO2. When sufficient amount of copper sulfide is converted to copper oxide, and copper oxide twice the amount of copper sulfide is present, it is a self-reducing agent, so it produces 6 copper and 3 SiO2. Friends, with time, copper sulfide gradually converts to copper while reacting with copper oxide. So with time, there are two distinctive layers of copper sulfide and copper. With passage of air, this copper sulfide layer gradually decreases and copper layer gradually increases. We call this copper, friends, blister copper due to its appearance. Friends, we know in this step, the heat is being generated by the conversion of copper sulfide to copper oxide. In turn, copper oxide acts as a reducing agent. This is a side blown converter, friends. We blow air from here, but not from the bottom. Why we don't blow from the bottom is, friends, we just now understood that this copper forms and there is no copper sulfide in this. So if we are blowing oxygen, there is little conversion of copper sulfide to copper oxide. So there is not much heat generation. So this copper may solidify and clog the holes of our tuyeres. Along with that, there is a chances of oxidation of our copper into copper dioxide as well, Cu2O. So to avoid those difficulties, we directly blow air into the copper sulfide layer, continuously converts into copper oxide, in turn gives us copper, which is blister copper, which is 98.5% pure. Now we got 98.5% pure blister copper. Now the first step of refining is, friends, fire refining. Here what we do slow oxidation to remove sulfur as sulfur dioxide, and here we do not want any oxidation of copper. But as we are blowing oxygen, there will be a lot of dissolved oxygen in copper, right? So there is another method called poling. This helps in removal of dissolved oxygen in copper with the help of generation of hydrocarbons. Friends, this method is very crude but very effective method. Here we take green tree branches and we stir the copper bath using these tree branches, and they generate hydrocarbons. They in turn help in the removal of dissolved oxygen from the bath. The next step in refining, friends, is electrolytic refining. Here we take impure copper as anode and pure copper as cathode. With time and passing electricity, copper gets deposited on this, and the impurities, or we call this anode mud, it gets settled under the impure anode. This anode mud consists of a lot of precious metals. They can be recovered later from the anode mud. So here we get 99.99% pure copper. So by this, our complete process of copper extraction ends. Friends, there are some other methods from which we can produce copper. First method is the partial or controlled oxidation of copper sulfide to CuSO4. This can be done using pore bed diagrams, friends. You know pore bed diagrams, right? From there, by controlling PO2 and PSO2, we can achieve the product phase of our choice. So then CuSO4 can be taken into aqueous electrolysis where we can produce copper, and another is CuFeS2 reacting with iron chloride, producing copper chloride and FeCl. Here also, this can be taken into aqueous electrolysis. There also we can produce pure copper. Other method is cementation. Friends, cementation is the deposition of less active metal by adding more active metal. We know out of copper and iron is more active. So what happens in the solution? Iron dissolves and forms FeCl3, where copper deposition takes place. All these methods are not as cheap as pyrometallurgy processes, but these are processes worth knowing. This is it in this video, friends. Hope you understood everything properly. If you have any doubts, please do comment. Take care. Keep smiling.